So I welcome you for the lecture series in the course Mechanics of Solids. And today, in the previous class, we'll just recap what we have discussed, that what is rigid body, what is deformable body, and where they are applied. These are all the things we have already discussed in the previous class, right? So in this particular session, we'll deal with the deformation of simple bars, right? What is deformation in bars? Deformation is nothing but whenever we applied external load, we start seeing the change of state in their particular length or shape or something like that. So that is called deformation of bars due to external load. So before the load, the original state, no external force is applied, it looks like this. And whenever there is a tension or compression, so either it may be a pulling force or a compressive force. This axial force pulls causes elongation, that is change in length, it is increase in length. And axial force pushes, that causes shortening, that is it is reduction in length. So deformation is the change in bar's length or shape due to applied force. Axial load refers to the forces applied along its length. So any engineering structure will experience either a tension or a compression or a shear, are the three major forces that is there for to deform in their shape, size, and everything. So let us see what is the basics of stress and strain. So let us consider a workpiece of length L, where the force is applied is F and the area of cross section is A. So then the formula stands in this format, like force per unit cross sectional area is called as stress. A sigma is nothing but force per unit area, and the strain we call it as change in length relative to original length. So this is a dimensionless ratio measures relative deformation. Why it is called dimensionless ratio? That is, both the denominator and numerator is of same length for mm and mm. So that two gets cancelled, so that there is no unit for strain. So we have seen what is Hooke's law and its elastic behavior. So within the elastic limit, the stress is directly proportional to strain. So whenever a body is subjected to stress, there is a strain, and at particular elastic limit, this strain, if is removed, or if the stress, the external load is removed, the stress is again coming to normal, and both stress and strain will be proportional to each other. So where the constant of proportionality is E, we call it as Young's modulus. Material stiffness constant. A material stiffness constant is very important, and it is not constant for all the materials. It may be a constant for particular material, but different materials will have different Young's modulus that we will go and discuss when we solve problems. And elastic deformation is bars return to original length upon load removal. That is what this Hooke's law is all about. So how will you calculate deformation in the bar? For example, a load is applied on the lengthwise, right? When longitudinal lengthwise, and the change in dimension is also in the length of the bar. Either when there is a tension, we will have increase in length, and when there is a compression, we will have decrease in length. But how will you calculate this change in length? That is delta L is formulated like this: force into L divided by area into Young's modulus. So deformation increases with force, that is directly proportional, and length, which is directly proportional, but decreases with larger area. So whenever the area is larger, the deformation is smaller. And stiffer materials, if the stiffness of the materials are more, then the deformation is less. So example calculation is given. For example, 2 meter long and 0.1 meter square area, load is 10,000 newtons. The Young's modulus is 200 gigapascal. They have asked to calculate this. tensile. Using this formula, you just calculate and then see what is the deformation of a bar. So we have something called as Poisson's ratio and lateral strain. Whenever there is a linear strain, there is also a lateral strain. For example, lengthwise there is a expansion of this bar, and widthwise it is the reduction in width, that is called a lateral strain. Axial loading causes both elongation and shortening and lateral contraction. This Poisson's ratio is nothing but negative sign of lateral strain to the longitudinal strain, typically 0.25 to 0.33 for materials. And real world applications are bridges, columns, cables. Everywhere we have simple bars, and there is also a composite bar that we see in the next lecture series. And predictable deformation, governing factors, safe design are the key takeaways from this lecture. And we have seen what is the foundational concepts of simple bar and stress and strain formula, elongation formula, and we have seen a calculation. I hope you all understood this particular topic. We'll see furthermore explore in the next lecture. Thank you.